на кружочек.
Трансляция пока красной не стала, да? О, стала. Окей. So, today mostly we'll set up some framework, notations, recollections for the would-be characters of GLN. But first I promised to make some comments on the green functions. The first example due to Tony Springer is the green function Q of trivial partition mu of any Q. And this is the Poincaré polynomial of the so-called Springer fiber B mu in the flag variety of GL n, but let's take it over complex numbers in order to speak about Poincaré polynomial. So first of all, what's this? So mu gives rise to some nilpotent element with Jordan type. E mu of Jordan type mu. Okay. And now, given a complete flag, zero in F1, in F2, and so on, in Fn minus 1, in Cn, lies in this Springer fiber if this particular fixed element well, kills this flag by degrees. So E mu of Fi lies in Fi minus 1. Okay, certainly it's non-empty. It's always possible to find such a flag. For example, just take the flag of kernels of powers or something like that, or images of powers, and take any refinement of this flag. And then it is known that cohomology of odd degrees of the Springer fiber vanishes identically. In fact, it is known that the Springer fiber has an affine paving, so it's a union of cells. Also, it is very, very singular. I'm not quite sure about this union of cells. The fact about vanishing of odd cohomology is true in any type, and there is so-called alpha partitional, something like this. But I'm not quite sure that it's known for E8 that it is really union of cells. But well, essentially it is. For all practical purposes, it is, but maybe not quite literally. So it's this, and I claim that q 1 to the power n mu of q is equal to the sum of whatever psi maybe I q to the power I, and this means that psi I is the dimension of cohomology in degree 2I of the Springer fiber. This is the meaning of Poincare polynomial. So in a sense, Q has degree 2. Yeah, so I started saying that this B mu is very singular. So for example, if mu is subregular, this nilpotent element is subregular, meaning that mu is n minus 1, 1. This so if it were just n, it would be most typical nilpotent element, yeah, in the open nilpotent orbit, so-called regular nilpotent element. And then the next regular is this. Then the Springer fiber is well, a tree of projective lines, namely like this: one projective line, another one, another one, another one, and finally. And so this well, it defines some graph. Yeah, I mean, this P1 intersects that one, and that one intersects those two, so you get a graph. And this graph is a n minus 1. Okay, so there are n minus 1 components, just linearly ordered. And it is, well, it is very general. I mean, for any other simple Lie group, it would be the same. I mean, especially if it's a simply laced Lie group, like D and E will have the same graph. It will be just some tree of P1s intersecting according to the Dynkin graph. If it's B, C, or F, it is related to the corresponding unfolding. Okay. What else do I want to say? That in particular, you see that the dimension of the zeroth cohomology is 1, and dimension of second cohomology is n minus 1. Okay, and in general, the dimension of top cohomology of B mu will be equal to the dimension of irreducible representation, probably V mu, yeah, the irreducible representation of the symmetric group. Well. Okay, so it's a number of some standard Young tableau. In fact, this is an old result of Nicholas Spaltenstein, that the number of cells in this paving is given by some numbers of Young tableau. Okay, so you see that it's all very closely related to representations of the symmetric group, and it is not an accidental coincidence, and in fact, this whole thing is named about Tony Springer because he constructed an action of the symmetric group viewed as the Weil group of GLN in this cohomology, preserving degrees. Okay, but this construction is well, was It is like 1975, something like this. And this construction was very, very non-elementary. It's absolutely non-transparent. So his construction used some, well, first of all, he did not even do this in 75. He only constructed it for GLN over finite field. And then he used, well, it was in Ital cohomology of this variety over finite field, and used some Fourier the linear, sort of geometric Fourier transform over finite field. And still it was very indirect. And then many people tried to understand this very mysterious construction, and finally Lustig succeeded in this in 1981. So first let me formulate the most general answer. So let me write the simple formula. Q rho mu of Q is the sum over I psi mu I of rho times Q to the I. So this is just definition of those coefficients psi. And then it is known that psi mu I, well, of W rho, so this is cyclic type, is the sine of W rho times the trace of W rho inverse in this cohomology. So this is the geometric meaning of the green functions I promised. Okay, and well, somehow I cannot stand the temptation to say a few well, highbrow words, scientific words about so-called character sheaves. In this relation, so by the end of April, we will hopefully compute the characters of GLN in a sort of elementary manner, at least without any sheaves. And without the Ital cohomology. And by the way, while we are here, let me ask you, what shall we do in May and maybe first half of June? So I understand that, so I could tell more about character sheaves, but I understand that not everybody knows about sheaves, and these are supposed to be Ital constructible sheaves over finite field, so maybe I shouldn't talk about this. I can also tell something about more general Hall algebras and their relation to quantum groups, but this will take maybe just a couple of weeks. Also, I could tell something about representations of GL2 maybe, but over p-adic field, local field. Well, I could also tell something about some specific Steinberg representation for any group, not only for GLN. So we'll discuss it for GLN, but it makes sense for arbitrary group, and it's somehow the most basic representation. But again, it can take up just a couple of a week or two. So do you have any preferences? So p-adic GL2 or what? Anybody? Any other? Anything else? For character sheaves, but maybe this is out of out of reach. Do you really know ethyl cohomology, for example? You do, but maybe you are the only one among us who knows ethyl cohomology. So, no other preferences? Well, then probably we'll have to follow your suggestion, unless you make some request. No, I mean, representation of the GL2 over p-adic field will take. So you understand that it's it's more serious than representation of GL2 over finite field, right? And this field, so it will take us at least a month, and there will be no more time for anything else. So it's irrevocable. Okay, so. What about character sheaves? As I said, hopefully we will succeed with characters of GLN, and for all the remaining groups, even for, say, for SLN, there is absolutely no elementary way to find the characters. Even for SLN, there is no elementary way to compute the characters. Well, except for SL2. For SL2, you had it in home assignment, but maybe for SL3, I don't know. But, well, in fact, I suppose maybe for SP4 it was also done elementary, but in an elementary way, but in general, no way. And the general strategy for arbitrary groups was designed and completed by Lustig and maybe Shoji. The idea is that, we construct ethyl constructible perverse so-called character sheaves. Over our group, say G over FQ bar, and there's an action of Frobenius, and it also acts on these sheaves. So F is equipped with the action of Frobenius. And then the fixed points of this Frobenius action on FQ bar is FQ. And so this is the finite group over finite field, our group of interest that we're trying to find the characters over. And then since this Frobenius also acts on this character sheaf, it makes sense to consider its action on the stocks at the fixed points. And there is a correspondence to some function on this finite set, finite group, just the trace of Frobenius, at the Frobenius, Frobenius, how should I say, the stock of F. Okay, so there is some function called, and this general idea to associate functions to sheaves in this way is due to Grothendieck, and it's called Grothendieck faisceau fonction dictionnaire. Okay, and the general principle is that the functions f for character sheaves are also called almost characters. And if G is GLN, then they're literally just characters. I mean, irreducible characters. But never else. Only for GLN. Even for SLN, it's wrong. And it is related to the existence of those very small representations. If you still remember, there were representations that I mentioned q plus minus 1 over 2. And also there were some sort of related classes, conjugacy classes. So there were 4 representations special in this respect, and there were also 4 conjugacy classes special in this respect. And the most non-trivial part of your computation of characters was for those representations at those conjugacy classes. And this, so there's some sort of 4x4 matrix, which is the most crucial part of the character values matrix for SL2. And for general SLN, this most crucial part will be n squared by n squared. Okay, but say for E8, there will be some various parts, and the most interesting part will be 39 by 39. But still, even if you take the group E8 over field F2, its order is more than the order of the monster group. So it's a huge, incredible, very big group. And its character table is also very big. It cannot even be printed. Well, no human can read the table of characters. But somehow it follows some patterns. And the most important and interesting part is this 39 by 39 part. And it's independent of Q. For any Q, it will be 39 by 39. Okay. So how, well, there is some procedure to compute those Grothendieck functions, almost characters, and there is another procedure how to go from these almost characters to real characters. So in this sense, the character table can be essentially computed for other groups. But for GLN, once again, there is no second part. You only need to compute the almost characters. And let me say a word how it is done. So to say, unipotent character sheaves for GLN. And well, again, as I said, for SL2, there were 4 very special characters and 4 very special conjugacy classes. The same here. There are unipotent conjugacy classes numbered by partitions, and there are also unipotent character sheaves also numbered by partitions. More precisely, they are numbered by representations of symmetric group. And again viewed as the Weil group of GLN. So, while you have your group, again, let's move to complex numbers for the sake of geometry. And it has some so-called simultaneous resolution. Again, due to Grothendieck. Though it was never, Grothendieck never wrote a word about this, but well, he has had many other words to write. But still, he discovered this, and then this, for example, Springer representation was just a consequence of this construction. So what is this? This is just the set of pairs G in G, and well, a flag F in the flag variety, such that G preserves the flag. Okay, and then, well, for example, if G is if your element small g is a central element, say identity, then certainly any flag is preserved by this. So the fiber of this projection, simultaneous resolution, is a is the whole flag variety. Now, what happens over so-called regular semi-simple elements? It means they're semi-simple and regular, meaning that all the eigenvalues are distinct. So, well, if you require that all the eigenvalues are distinct, then your element is necessarily semi-simple. So you don't need to say this. So what's the fiber? Let's compute.
Just the eigenvectors? Well,
Yes.
I don't know how to say it.
Just it's ideal space by one.
Yes. Well, it is finite, first of all. And Sn acts on this simply transitively. Yes, so as Ira and Misha say, you just you do have all the distinct eigenlines, and then you form this flag by randomly choosing the first one, then adding the second one, then adding the third one, and so on. But then you can reorder them, renumber them, and you will obtain the action of symmetric group on this fiber. And this is, well defined in the family. So there is an action if you take regular semi-simple part and its projection to regular semi-simple part. So this is an SN Galois covering. Well, unramified. But as soon as you go out of regular elements, you have bigger fibers, higher dimensional fibers. So the whole thing is not Galois, is not a covering by any means. Only on this open subset. Okay. So now you take the constant sheaf. Well, these are coefficients. Well, I don't know. You may want something other than the complex numbers here. I mean, there's some ground field where a group is defined, and there's a field of coefficients which is different. For example, for talco homology, these coefficients will be a Lyadic sheaf. So say you take this constant sheaf Q on the Grothendieck simultaneous resolution, you take its push forward to G. And well, this is this is the derived push forward because you have some higher dimensional fibers. So this is some complex of constructible well, maybe I should say constructible complex. Let me say constructible complex. Of sheaves on G. Okay. And you know that when you restrict this complex to the regular semi-simple part, then this is equipped with the action of symmetric group and well, I don't know how to say this, but it's isomorphic to the group algebra of the symmetric group, if you wish, on GRSS. Okay, so there is an action, stock-wise action on the sheaf. Okay, but no, maybe I don't know how to say this. I don't mean that as a constant sheaf. It's not a constant sheaf, but well, say is a local system. And the local system is the same as representation of fundamental group, but this fundamental group has a quotient sigma Sn, and this Sn acts regularly on this regular representation of Sn. Okay. And now, well, as a result of Kazdan and Lustig attempt to understand Springer construction, there was a theory of perverse sheaves created, and well, it turns out that this is a perverse sheaf. So it's a complex, but it's a very special complex. And such special complexes are called perverse sheaves. This perverse sheaf, well, is equipped with an action of the symmetric group extended from the open part okay. So this action is just somehow stock-wise. This symmetric group does not act on the base on the group. It only acts on the stocks of our sheaf. And this action from the open part, where it is tautological, extends to everywhere else, for example, to the identity. And on the identity, you know that the fiber was the flag variety, and so the stock of this sheaf is the cohomology of the flag variety. So hence, Sn acts on cohomology on all the stocks. Well, okay, on all the stocks of this direct image. And this is nothing but cohomology of the Springer fibers. But just by the base change, whatever, for any element G, well, in particular, on the cohomology of Springer fibers over unipotent elements. Okay. And this is Lustig's construction of Springer representation. So this is why the symmetric group acts in cohomology of Springer fibers. Okay, and finally, so these perverse sheaves they form an abelian category. And this particular guy can be decomposed as an object of this abelian category with the action of symmetric group just into isotypical components. So these are just isotypical components. Okay, so these are again perverse sheaves. So finally, what I wanted to say is that they are the unipotent character sheaves. Is an irreducible unipotent character sheaf. And if you apply to it this Grothendieck construction, you just obtain a unipotent character of GLN. So the trace of Frobenius in this particular guy. It's an irreducible character of GLN. Okay, and which one? Well, you know that you can take induction from Borel subgroup to GLN, to G, of the trivial representation. Well, these are our coefficients. Well, now it's not very good. Okay, but still, at least for GLN, this will work. You can work with Q. In general, you'll need some extension. But we take this, and you know that this is, again, direct sum over irreducible representations of the Hecke algebra. Yeah, probably home assignment of January 31st. And I don't know how to note them. Well, let me call them V calligraphic, M tensor sum representation of GLN. Well, maybe let me call it rho M. Okay, so these are irreducible representations of GLN. Unipotent representation of GLN. Okay. And now, if you remember something from January 31st, this Haker algebra was given by some generators and relations. And there were cubic relations for the braid group, and quadratic relations, which were sort of deformation of relation that S square is 1 for symmetry group. So all in all, this Haker algebra, it has the size of symmetric group, I mean dimension and factorial. And it is just some deformation of the group algebra of symmetric group with parameter q. Well, q is actually a prime power, but still you can view it as a formal variable. Hn well, of q is a deformation of the symmetric algebra, group algebra, maybe q of Sn, well, with parameter q. But you also know that it's semi-simple. Right? And this algebra is semi-simple, and semi-simple algebra does not really deform. It's rigid. And so, just on some general grounds, this Hn is absolutely isomorphic to the group algebra of this. So it's really difficult to produce an explicit isomorphism, but it's absolutely isomorphic for these cheap reasons. Okay. In fact, an explicit isomorphism was also constructed by Lustig in some very non-elementary way. But at least it follows that the irreducible representations of this Haker algebra are also numbered by partitions. Okay, so in this sum, the parameters M are just partitions. And now I claim that this V, no, rho, how to say it? Rho mu, or maybe the character of rho mu is equal to the trace of Frobenius function of the corresponding character sheaf. That's it. So, so there are two very different procedures which produce the same answer. So on the one hand, you geometrically, you know nothing about this Haker algebra. You just consider this Grothendieck simultaneous resolution. You take the push forward of the constant sheaf. There is an action of symmetric algebra. You decompose with respect to this action of symmetric algebra. And you take the trace of Frobenius function. And you are done. On the other hand, there is absolutely non-geometric, very elementary procedure. You induce from Borel to GLN over finite field from one finite group to the other finite group. You decompose this induced representation just from general patterns. Because you know it's an endomorphism algebra. Endomorphism algebra is Haker algebra. And then the result is the same. So you decompose, you take the component numbered by mu, and this component corresponds to this geometric construction which knew nothing about Haker algebra. On the other hand, this construction somehow does not know anything about the symmetric group action on the Springer resolution. But they give the same result. Well, something similar happens for arbitrary groups, but with serious complications. Okay, so now we can forget all about this and start our preparations for characters. Right here. By the way, I forgot, there was another option, but not about representations of groups, but about combinatorics. Because those whole Littlewood polynomials, as I mentioned, they have one more deformation, Q deformation, McDonald polynomials. And it is a very rich theory, so I could talk about this in May, June.
Ask us again, please.
When we end all this, but then I somehow have to prepare. But okay, so I will ask again in a couple of weeks. But so the options are once again say representations of GL2 over local field, McDonald polynomials. But this is in the spirit of what we did for whole Littlewood polynomials. It's just pure combinatorics. I mean, in fact, they do have some geometric meaning, but we will not have time for this. And these are major topics, and there are some also minor topics, which will not take up all the time. Like what Steinberg representation, and whole algebras for say ADE quivers.
Actually, I like 3 and 4 more than that.
But they may not take up all the time. It may, and then I will not have time for anything else. So it's not an easy question. Okay. Okay, so just we'll set up notations for the study of characters. Of GLN. So K will be our final field. K bar will be its algebraic closure, and there will be Frobenius automorphism, namely x goes to x to the power q, and K n will be the degree n extension. That is the fixed points of Frobenius to the power n. M will be the multiplicative group of the algebraic closure, and Mn will be the multiplicative group of the degree n extension. So again, the nth Frobenius fixed points in the whole of M. Now we have inclusions of such fields. So if n is divisible by m, then we have an embedding of those multiplicative groups, but also have the norm map from n to m, from mn to namely x goes to x to the power q to the n minus 1 over q to the m minus 1, or else the product of all the possible Frobenius powers, because the Frobenius generates the Galois group of this extension, and D is the ratio n over m. This, in fact, is surjective. Okay, and we will consider the inverse limit k of those norm maps, and the well, it's denoted z hat of 1 of k bar. Well, it's just some notation, but well, standard notation from Étale cohomology. And well, just as an abelian, well, it's an abelian group, as you can see. And what is this abelian group? Well, it's not just an abelian group; it's a profinite abelian group. So it's topological compact abelian group, and there are not very many compact abelian groups. So what is this? Of powers of what? Yes, but this is the inverse limit. So if we took the colimit, the union, we would just obtain, yeah, all the roots of unity, and in fact, all the finite field, but multiplicative group. But here we take the inverse limit, so obtain really some compact group. And what is this compact group? Pardon me? I cannot understand what you say. Galois. Yes, it's isomorphic to some Galois group, that's true, but well, I ask most explicit description. What compact abelian groups do you know at all? Do you know any? Pardon me? What? S1. Yeah, that's good, but S1 is connected, and this is profinite, so totally disconnected. So what totally disconnected compact groups do you know? Right, absolutely. So that's it. So it's the product over L not equals to P of ZL. Yeah, P-adic. Well, L-adic. Yeah, because we are recursive P, so our roots of unity are never P through roots of unity. The degree can be arbitrary, but prime to P. Okay. But somehow the Frobenius acts here naturally and does not act here naturally. So this isomorphism is not canonical, so say, meaning precisely that not well compatible with the action of Frobenius, and well, this one somehow designates this particular action of Frobenius that's actually taking place. Okay, so now we also define L as the dual group, Pendragon dual group. So since this was compact, this one is discrete, and this is the colimit of Mn dual. But now each Mn is a cyclic finite group, and so it's abstractly isomorphic to its dual, but not canonically. Yeah, and so again, non-canonically, this is isomorphic to M, right? Well, the limit of its degree q to the n minus 1 subgroups. Well, this is the roots of unity, as Michael said. Okay, and now what do I want to say? Yeah, I say that what is actually canonically true M is not equal to L, but to its dual, and maybe I should say Q over Z mod tensor over Z hat with L dual. Okay, and reciprocally L is Q mod Z tensor over Z hat M dual. Okay, and this is denoted as Q mod Z of -1 of K bar. So the dual, well, if we forget the action of Frobenius, then the dual of Z hat will be Q mod Z. Do you know this? Maybe we discussed this already, yeah? No, didn't we? At least half a year ago we discussed this. Yeah? Well, also say, if I take particular ZL, dual is QL modulo ZL. And then I just take the product, so to say. Okay. So there is a Frobenius action. L, namely xi goes to xi to the power q, and Ln is the fixed points of Frobenius to the power n, as always, and L is the union of those fixed points, and Ln is dual to Mn. So I have a pairing. Ln times Mn to complex numbers denoted by brackets like this. Now, if again m is divisible by m and d is the ratio, then xi lies in Lm and inside Ln, and x lies in mm inside mn. So we can pair them in two different senses, and the pairing of xi and x number n is equal to the pairing number m raised to the power d. Okay, so finally, phi will denote the set of orbits of Frobenius in M. So any such orbit looks like powers of some element. Where x to the power q to the power d is x, and the polynomial f, the product from I equal to 0 to d minus 1, t minus x to the power q to the I, has the coefficients in our ground field of q and is reducible. Okay. Conversely, well, any irreducible polynomial with a leading coefficient one, except for a unique polynomial this, because this is not invertible. I mean, its root is 0, and we don't, well, we want to consider multiplicative groups without 0. Well, arises this way. So the set of orbits is a natural bijection with irreducible polynomials with leading coefficient equals 1, but not t. Okay. Now let us classify the conjugacy classes in GLN. So Gn is gln of k. And given an element G, we obtain a structure of k of t model on k to the power n. In fact, we already discussed this a few weeks ago, but so first let's recap this and also set up the actual notations. And for two elements in Gn, they are conjugate. If the corresponding modules are isomorphic, maybe let me call it V. So Vg is isomorphic to Vh. Okay. And so, well, a conjugate is a class. C in Gn gives rise to an isomorphism class say Vc over k of t modules. Okay, but this Vc certainly is decomposed into direct sum of indecomposables. And each indecomposable looks like the quotient modular some irreducible polynomial raised to some power. Something like this. Okay. And so here f is an irreducible polynomial, not divisible by t. Well, I don't know how to say it. Those f's are kind of various different, and m's can be various different. So, how to say this? Well, all in all, we get a collection of partitions mu. So for each irreducible polynomial, we obtain its own partition. So we will collect those powers, well, corresponding to our particular f. Okay, and well, mu of f is a partition mu1 of f, mu2 of f, and so on. And now this module Vc is the direct sum over all the possible f and all the possible I, the indecomposable modules f to the power mu I of f. Okay, and what we know is that the total size of mu, well, defined as the sum over all irreducible polynomials, degree of this polynomial f times the usual size of partition mu of f must be equal to n. Okay. Well, conversely, given such function into partitions of the total size n, we produce